Okay, so we are going to do Plonk and Plonk on stage. So I need to run Jupyter Lab, and you should open. All right. So this video is about doing Plonk by hand, or not exactly by hand, using Sage Math. And we're going to do a very simple circuit which checks that you have a solution to the equation x squared plus y squared equals z squared. So you have basically an example of Pythagorean triangle with integer numbers. So send this one to somebody else. It's inspired from is pretty much the same as this Plonk by hand, and it's also coming from the Vitalik article about Plonk, understanding Plonk. But these two things are what we're going to use. So let's start a new notepad. And we use SageMath. The underlying group that we're going to use for numbers is all the numbers between 0 and 100. So that's z over 101z. 101 is a prime number, so we are guaranteed that every number has an inverse in that group. And the group is not super big, so we can do most of the stuff without too much issue. So to use that group, this is introduced by integer modeling. So we do integer modeling 101. And let's call it F101. All right, so in this group, if you have a number, you will call it integer mod of that group, and then something 5. So it's 5 in this group, and that's 5. So the cool thing is you do -5, then it's going to tell you that it's the same as 96, because -5 plus 101 equals 96. And you can also find inverse, like 1/5 is 81. So this group is pretty cool because -1 is easily found as 100. So if you do -1, you can see it's 100. And therefore, if you do -1/5, it will be 20. So 1/5 would be -20, which is 81. So most of the stuff you can calculate by hand, especially like things like half. Half is -50, therefore it's 51. So 1/4 is 25, and it would be 76. Okay, so that's one advantage of this group. And the elliptical curve that we're going to use is this one here. Don't say it. It's x. So they all form y square equal x cubed plus x plus b, but we are going to use a equals 0 and b equals 3. I like this one because this way, if you do 1, then to give me 1 cube is 1 times plus 3 is 4, and then y is 2. So you have 2 easy solution, which is 1, 2, and 1 minus 2. So to define this curve, we can use this syntax. Elliptical curve. Then the group 101, and these are the parameters. 0 is b, and no, A, sorry, 0 is A and B is 3. So I can do this way. And it tells us that this curve y2 equal x cubed plus 3 defined over integers modulo 101. Right? So let's call it E. Then on that curve, you can list the points, see all the points, and you can see that they are given in homogeneous coordinates. So they have actually 3 coordinates. But you see the last one is 1, unless we're talking about the point at infinity, which has 0. And to convert between homogeneous coordinates and affine coordinates, you simply divide each x and y by this one z. That's why if you divide by 1, it won't change anything. So these guys are pretty much the same as affine coordinates, except for the first one, because you can't divide by 0. So this one is the spatial point. You see that we have 1, 2, and we have 1 minus 2. Then 9 is minus 2. And then you have a bunch of other points. All the points are not going to be there. So for example, you don't have any solution for a point that has x equal 2 or x equal 4. There are no points there. That's because this curve is, we're using F101 on this curve. It's not going to completely define all posits or abscissa. So we have to extend the field to contain solutions to polynomial that has that wouldn't be in that wouldn't be in F101. So let me remove this one. It's a bit too much. Delete cell. Okay. So F101 has the normal numbers, but you can extend that field kind of the same way you extend the field of real numbers to complex by adding a special value, which would be the solution of a polynomial that normally has no solution in the original field. So what they use is so any polynomial that won't solve in F101. So for example, if you have a polynomial, they use x squared plus 2. We can't use x squared plus 1 because x squared plus 1 is the same as x squared minus 100. Right? X squared is the same as x squared minus 100. Sorry, x squared minus 100. Because and then because minus 1 is 100, right? So that is factorizable into x minus 10 multiplied by x plus 10. And therefore 10 and minus 10 are solutions. But if you do x10 plus 2, then that is irreducible in F101. So we are going to extend that field F101 with solution that we call it. Let's call it solution. We call it solution X. I think they call it X. Yeah. Okay. So to do that, we define. We define this. So that's the Galois field. So Galois field of over 101 is the same as modular ring over 101, but over 101 square, then you have to put another. You have to give the what would be the solution of the polynomial solution. So if you do this one, oops. What's the problem here? Oh, you have to define what is x. All right, sorry. So you have first to say that X is a polynomial ring over 101. So let's do this over F101. Right, and then that we extend that field to K with the Galois field over 101 and with solutions. But so this solution, so we have now to every point would have can be written as a pair of A plus UB. That's the x coordinate, and the y coordinate can also be written as A plus UB, a different one, of course. So now, if we do the elliptic curve over K, so we have E2. So that's the extension of E over K. Right, now we have E2 that also has the points of E, but it would also have the have all the points of E, but also have points that are outside. Right, so you find the 1, 2 still there, and 1 minus 1, and now we have a solution at coordinate 2. So this one is x equal 2 and y equal 34 times x, and this x is this special value which squares to minus 2. And because the embedded level degree of this curve is 2, we don't need to go farther than that. All right, so this can explain here. Embedding degree. So first, we should find actually the order of the elliptic curve. So let's remove this stuff. Cell. So to find the order of E, first we get a point. So the point we have was 0, 1, 2, right? So G is our generator, and we can calculate G plus G. That's another point. To do this by hand, you have a formula, which is this formula. This formula is the same as for all elliptic curve, except that our has A equals 0, so it's even simpler. So this is the formula. You define M equals 3x2 over 2y. So I want to double this point, and we say M equal 3 times 1, so 3 divided by 2 times 2, so 4. M is it has to be inside this ring, right? So we have to do integer mode of 3/4. Right, and then M would be 26. That's what really they should find the same value here. So to G, M equal 26, and now we do M square minus 2x. Now M square. So same thing. It has to be in this ring, right? M square minus 2x. X was 1, so that should be enough. And let's give me 68. So that was 68 here. So the other value is M times 3x minus M2. M. Oh man, how to 3x and M2. 3x. So 3x is 3 minus M2. 76. Oh, that's not that. Oh, and then minus y. So and then minus 2. Minus 2. Okay, so 74. So we see that the point is 68, 74. So we don't need to do this by hand anymore since this library takes care of it. And we can express all the multiple of G like that for E in range, let's say range 20. So that gives 0 times G, which should be our point at infinity, that's 0. And then G, 1 to 1, 2G, 3Gs, and eventually it should repeat. It will repeat. So you get all this guy, and then you get 0 again here, right? So that gives us that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 17 times G is 0. That means that the order of the curve is 17. So that's what they found here as well. And 17 is a prime number, which means that everything is so you can compute everything from 17 from the G. Okay, so that's also there's a formula to find the embedding degree. That's the lowest number k, such as R is our 17. It divides P, which is 101, power k minus 1. And then we can find it. Okay, so we can find it by saying 101 square minus 1. And then we can see if this is if you can divide this by 17. So I will divide by 17 here. And you can and we see it's divisible by 17. So our embedding degree is 2. So that means we just need polynomial of degree 2, GF of 101 square. So only 2 coordinates and only one polynomial here is sufficient. Polynomial of degree 2 is sufficient. Okay, so what have we learned so far? We learned that the degree, the order of the elliptic curve E is 17. So N is 17. Let's store this. We have a generator of E. Now we want a generator of G2. Right. So so we can do points. What's going on here? Oh, sorry, not G2, E2. And so the point they have chosen, and I'm going to choose the same one. Any of these points will work. Of course, not the point that is already in G. So, for example, we can take this point. It's fine. But they used which one? So good one. 31, 36. Actually, it's a typo. They meant 36, 31 because we can see here that 31 is not the right one, right? So 36, 31 is the right one. 36, so that's x, and the y is 31 times u. They call it u, but here it's capital X. So that's G2, this one. And we're going to call it G2. G2 equal E2 of 36 and 31 times X. Okay. So delete these cells. I don't need that. All right. So we have G and G2. Then the trusted setup is to generate what's the name? SRS, structured reference string, which are basically the multiple of G up to n plus 2, where n is the number of gates of our circuit. And they say that the circuit we're going to do, they need how many? I forgot. Wow, how many they need? They need 5, I think. Okay, that's how many? 1, 2, 3, 4, 5, 6, 7. 7 plus 2. Right, so this was a generator of G. So these guys are easy. We can do it by doing the stuff we did before, actually. I plus 1 times G for I in range, how many here? 3, 7, 7. So that should give us 1, 1, 2, 68, 74, 65, 98. Oh no, it has to be a power, right? A power of. So they choose a random number, and it fired out, and it was 2 randomly, and that's so that's a power of 2s, right? So actually, this is not that guy. It's I times I power not 2 power I times G, right? So 1 to 1, that's still the same guy, right? 68, 74, and then the next one is 4G, 1G, 2G, 4G, 8G, and so on. 65, 98, 18, 49, 199, 68, 27, 65, 3, and 65, 3, guys. So these are all the G's. And now we need the same thing, but with G2, and we only need 2 of them. So we do the same with 2, and now it's G2 here. So 36, 31. It's still a typo here. It's not 31, 36. And 90, 82. 90, 82, this one is right. Okay. It's kind of strange that they have a typo and they repeated the typo, since there's no way they can get this one if it was this number. This number is not. It's not gonna be on a curve. This one is on the curve, because if you do 36 cube, and then plus 3. Oh, it has to be. It has to be on F1, right? So it has to be also integer mode of this guy. That's 98. And if you do 31, the x cube by 3, you do this, but with 31 square. So this is 31 square. And then you also have x square. X square, we know it's minus 2. So multiply by 2 and the number minus. Yeah, 98, 98. So this point is really on the curve. Whereas if you go 31 here, that's 100, and 36 here, 34. This point is not. Okay, so delete these cells. All right, so we have, so our trusted setup is these 7 points plus these 2 points. These points here. Okay. Well, the next step is to do the circuit. So the circuit they want is to they want to have a circuit that checks this equation. The equation is okay. So all the gates that we have are multiplication gates, addition gates, and okay, so they call x1 A, x3 is going to be B, and x5 is going to be C. You do x1 times x1, you can do that. Multiplication of 2 inputs gives you an output, x2, x3 squared is 4, x5 squared is x6, and that x2 plus x4 is equal to x6. Right? So this is which is the same as saying that x1 squared plus x3 squared is equal to x5 squared. Right, so that guy here. And the assignment of x1, x2 to x6 is a sweetness, is a solution. So for the case where you use 3, 4, 5, 3 would be x1, x2 is x1 squared, so that's 9, and 2 is 16, and 5 25. And you do have the fact that 9 plus 16 is equal to 25. All right. Now there's this conversion where each row is going to be of this form. So it looks a little bit complex, but really what it only means is that if you want to do a multiplication, you use QM. If you want to do addition, you use these guys. And if you want to add a constant, you use this guy. All right. So the first gate is A1 is A1 and B1 are X1. So you do, this is going to be X1 times X1. So X1 squared. And the output C1 is X2. So X1 squared minus X2 is equal to 0. That's the first line. Then you do the same thing with X3. X3 squared minus X4. And then same with X5 squared minus X6. And finally, you have the fact that the addition of X2 plus X4 minus X6 equals 0. No. So only thing that actually isn't captured by this is the fact that the output C1 is the same as this guy A4, right? A1 is C4, C2 is B4, and C3 is C4. Yes, that's what it is. So that's what's going to be called the copy equations, the copy variables. All right. So far we did that, right? So you write this. It's quite very simple, and then you extract that to be these vectors. QR is 0, 0, 0, 1 because you take 0, 0, 0, 1. QR is 0, 0, 0, 1 as well, right? QO is minus 1, minus 1, minus 1, minus 1. And QM is 1, 1, 1, 0. 1. What? 1, 1, 1, 0. Oh, there's a typo. It should be 0 here. And QC is 0, 0, 0, 0. Right? So there's a typo here. QM should be 0 here. All right, okay. And that's part 1. That's the setup.